Let's consider in this example bungee jumping from a bridge. We'll have a 70-kilogram male bungee jumper that jumps from a bridge. He's tied to a bungee cord that has a length of 12 meters when it's unstretched and falls a total of 50 meters from the bridge. Assuming Hooke's law applies to the cord, we'll have two questions. Part A, to calculate the cord stiffness or spring constant K of the bungee cord, and B, to find the maximum acceleration that the jumper experiences. We will have two potential energies here, gravitational and elastic of the cord. So in preparation for that, let's put our axis, vertical axis Y that goes upward. Then I'll start marking vertical elevations at different instances. Usually a convenient choice of 0 will be either the top or the bottom. Here I will choose the bottom or the lowest position where the jumper reaches as my Y0 mark. That marks the bridge as the Y50 meter mark. Somewhere here, 12 meters below the top or 38 meters above my 0 is where the cord begins to stretch. So it's very important to see that the cord is not stretched from the very top, but 12 meters under the bridge. So here I will mark that the stretching of the rope or the cord is 0 here, 12 meters below the bridge. That means that by the time the jumper reaches the bottom, the cord will have stretched 38 meters already. So with that, I'm actually ready to look at the total mechanical energy. At the top of the bridge, I will have kinetic plus 2 potential energies. Starting from rest, of course, the kinetic energy will be 0. The gravitational energy will be mgy. Here y is the 50 meter, the vertical elevation of the bridge. And I'll have no elastic potential energy yet because the cord has not begun to stretch yet. At the bottom, at the Y0 mark, at the lowest location that the jumper reaches, the total mechanical energy, being kinetic plus 2 potential, again will give me 0 for the kinetic. This is a turning point, a point of return where the jumper stops momentarily and then is being pulled upward. The gravitational energy, mgy, of course, again will be here will be 0 because I chose that location to correspond to y0, and then I'll have to add simply the potential energy due to the elastic cord, 1/2 k times delta x squared. Here delta x is the stretching at the very bottom. When I apply the conservation of energy principle, I will have the total mechanical energy at the top of the bridge, which is mgy at the top, has to be equal to 1/2 k delta x squared at the bottom. Numerically, that will be 70 kilograms for the mass of the jumper, 9.8 meters per second squared for the gravitational acceleration due to the Earth, 50 meters, the height of the bridge has to be equal to 1/2 the unknown elastic spring constant of the cord K times the stretching at the very bottom, which is 38 meters squared, which gives me for the spring constant or the cord stiffness K to be 47.5 newtons per meter. Now let's see what happens, how to solve question B. In question B, we need to find the maximum acceleration, but before that we have to decide where that happens. That will happen in the extremes, either the top or the bottom, but let's analyze that motion step by step. At the very top, when the bungee jumper jumps, he will be in free fall, so we know the acceleration of him will be 9.8 meters per second squared, and it will be pointing downward. Somewhere, well actually exactly at the 38 meter mark above the bottom, or 12 meters below the bridge, the rope or the cord will begin to stretch. And this is where we actually have to consider two forces acting on the jumper. It's not a free fall anymore. We will have the gravitational force mg, but we will also have the elastic force coming from the bungee cord, which following Hooke's law will be k delta x and pointing in the upward direction. Somewhere the bungee jumper will reach a point of equilibrium where the two forces will be equal in magnitude. Here I can apply Newton's second law. The net force will have to be equal to the m times acceleration in vector form. And in terms of the vertical components, which is all we have here for the forces, I will have a negative vertical component for the gravitation force, minus mg, plus the positive vertical component from the elastic cord, k delta x, has to be equal to ma. If this is the point where the two forces are in equilibrium, that will be equal to 0. But beyond that, we will actually have an acceleration. Let's consider what happens at the very bottom. I will have still the same amount of gravitational force, mg, but now the elastic force of the cord will have increased proportionally to the stretching of the bungee cord. So it will be k delta x, and that will be the maximum stretching, so that will correspond also to the maximum elastic force that I will see during the process of the entire jump. Newton's second law here gives me minus mg plus k delta x max, this is the maximum stretching, will have to be equal to ma. And so possibly if the acceleration, if we have a maximum acceleration, that will happen here at that extreme case. So I have marked it as ma max. Remember here that k is the elastic spring constant of the cord k, which we found in part A, 47.5 newtons per meter. So I'm ready to actually put the numeric values in my Newton's second law equation. With that, I will have minus 70 kilograms for the mass times g, which is 9.8 meters per second squared, plus k, which is 47.5 newtons per meter, times the stretching of the cord, 38 meters, has to be equal to m, 70 kilograms, times the maximum acceleration, which gives me for the maximum acceleration to be 16.0 meters per second squared. And notice that this is upward now. The elastic force is exceeding the gravitational force and causing that acceleration to be upwards. One final subtle point here is to check actually versus the acceleration at the very top of the bridge. There is no reason why the acceleration at the bottom has to always be larger than that the bridge. It is possible that we might get a maximum acceleration during the stretching of the cord that is still less in magnitude than the original free fall. As it stands, however, in our problem, at the very top we have, during the free fall, we have 9.8 meters per second squared downward, and at the very bottom we have an acceleration due to the combination of gravitational and elastic force, 16.0 meters per second squared. So that clearly is the larger acceleration in magnitude. So the answer stands that the maximum acceleration occurs at the very bottom of the jump, where the jumper stops momentarily, and is equal to 16.0 meters per second squared upward.